Hi folks, Mr. Ackerman here. Thanks for watching. The topic of this video is projectile motion, and it's the first part. I'm going to do this in two parts, so there will be a second video. The first part here deals with what are called horizontal launches of a projectile, and the second part will deal with what are called non-horizontal launches. So before we launch into projectile motion, haha, bad physics joke, now you know I'm a physics teacher, not a comedian, we've got to talk about what is a projectile. So first of all, you probably have some thoughts of your own about what we mean by a projectile. It might be something flying through the air, like maybe a rocket or a bullet or something like that. And you're on the right track. However, before we do any discussion of the physics of projectiles, we have to talk about the physics definition of a projectile, because physicists have a very specific definition. So let me give you the definition. The definition of a projectile is an object that's moving through the air where only the force of gravity is acting on the object. So now I'm going to ask you to think of a number of objects that move through the air and ask yourself, is gravity the only force acting? So, for example, if you see an airplane going through the air, is gravity the only force acting on the plane? Think about that for a minute. Pause the video if you have to. Okay, well, thinking about an airplane, you don't have to be an aviation expert to know that an airplane has engines, and those engines keep pushing to cause the airplane to go forward, to make it move so fast. So right away, airplanes have more than the force of gravity acting on them. They have what's called the thrust of the engines. So no, airplanes are not projectiles. How about a ball thrown through the air? You might be thinking, well, if as a ball goes through the air, you have to push on it, you have to throw it. And you'd be correct. You have your hand, the force of your hand on it. We're actually not talking about what gave the ball the initial push. We're talking about once you let go of the ball. So once the ball is in the air, you're throwing it to your friend, is it a projectile? Well, what forces are acting on it? There is gravity, of course. There's also some wind resistance. If you've ever tried to throw a ball, you know that the air can push on it. It can make it deviate from its intended path. In this section of grade 12, we're actually going to neglect air resistance. Even though we discussed it in the last textbook section, we're going to ignore it for now. So let me add in the stipulation that we're talking about an object like a ball moving through the air with no air resistance. In that case, would this thrown ball be a projectile? And now the answer is yes. The only force acting on it after you let go of it with your hand, the only force acting on it is gravity, and therefore it qualifies as a projectile. Same thing goes for a bullet, for example. The gun gives it an initial push, true, but once it's out of the gun, if we neglect air resistance, gravity is the only force. How about a rocket? Would a rocket qualify as a projectile? Here, like the airplane, the rocket expels hot gases backward, and according to Newton's third law, those gases push the rocket forward. Therefore, no, there is more than gravity acting on it. A rocket is not a projectile. So, just to be pretty basic, let's start thinking about things like soccer balls, footballs, baseballs, golf balls, bullets, things like that as projectiles. And what we're going to do in this section is talk about how we make these calculations about the different characteristics of a projectile, and I'll get into those shortly. For those of you following along in the homework schedule, we are in lesson 3. The section is 1.4. As I mentioned, there are two parts to this. You're watching part number 1 right now. Along with this video, in order to be totally prepared for class, make sure that you're taking notes on the textbook section and pay attention to the sample problems that relate to horizontal launches. In class, I'm going to do a demonstration for you. We're also going to work on some homework problems that you see here. And before we do the non-horizontal launches, we're actually going to do a lab. It's a fun lab called the ball bearing bounce. It's in your course pack on pages 4 to 6. And I'm even going to introduce you to a topic that we need to use when we're analyzing lab results. This is called experimental uncertainties. So this part right in here is not just related to projectile motion. It's actually a general lab skill that you learn as you go through the sciences. It's called dealing with experimental uncertainties, and I'm going to introduce it to you in this lesson. All right? Extra homework to practice later, horizontal launches, a lab report on the ball bearing bounce. Parts of it will be handed in. I'll tell you what parts in class, so pay attention. All right? Without further ado, let's move on to our first slide here. And you see an interesting picture. It seems like superimposed photos of a guy taking a jump on a motorcycle and landing, hopefully safely, on the other side. This would be an example of a projectile. If we neglect the effects of air resistance, yes, the motor was pushing the bike and the rider on the ramp, but after he leaves the ramp, there is no more pushing from that motor. It's just gravity. So here's an example of a projectile. And of course, this is not a horizontal launch. A horizontal launch would be like going off the ramp somehow horizontally like this. This is a non-horizontal launch. It's launched up at some angle theta to the horizontal. And so actually, while this is a really interesting photo, we're going to talk about this in part 2 of the video, because remember, part 1 is only about horizontal launches. But I thought I'd show you something interesting there to get you started. And there's also some information we can get from this. Like, if you look at this, you can see that the guy on the motorcycle goes a certain horizontal distance. So you're going to see, for horizontal distances, you're going to see me writing delta D, which you're familiar with, but now you're going to start to see a subscript x for delta dx, talking about horizontal displacement. And for that matter, there's vertical displacement, so be prepared for a symbol like delta dy. Okay? You might also notice that since this guy goes off the ramp with a certain initial velocity, so that's v1, thinking back to what we know about vectors, they have components. So I'll use a different color here so you can see a bit better. There is a horizontal component to this vector, and there's a vertical component to this vector. We could call that vx, and we could call this vy. So get ready for velocity symbols that contain a subscript x and y as well. All right, I'm going to leave this for now, and we're going to go on to the next slide. In here, I have a picture which is right out of your textbook. The textbook we're using is Physics 12 by Nelson, to give credit where credit is due. This is figure 4 in section 1.4. I want you to study it for a moment. I'll tell you what it's about. Imagine two balls, one probably colored, I don't know, maybe it's colored red. This is a black and white photo, so you can't tell, but let's assume it's red or something like that. And another ball that's maybe silver or white. It's coming up a lot brighter. Now, what happened in here, and I'm actually going to demonstrate this for you in class, is there's a device that actually can, at the same instant, drop one ball. That's the ball you see falling here vertically, the one that might be red. And the other ball is fired horizontally. They're released at the same instant. So we have here a drop and a horizontal launch. Now, why are you seeing so many images on the screen? Well, that's because of the way the photograph was taken. This photograph was taken in a very dark room with a black background. And what the photographer did was he or she had a strobe light flashing, and the strobe light flashed at regular intervals. We don't know exactly what those intervals are. They could be 1 every 10th of a second, or 1 every 5th of a second, or 20th of a second, who knows. But whatever the number is, what it does is briefly illuminate where each ball is at the same time. So you're getting sort of a stop-action record of what happened. It's almost like a two-dimensional ticker tape, if you remember those ticker tapes from grade 11. Anyway, what does this tell us? Well, first of all, think about what you know about a dropped ball. The ball that I'm pretending is red, I'm going to circle that here in red to help you keep track of that. What do you notice about this? This is a dropped ball. What do we know about a dropped ball? Well, that's easy. If there's no air resistance, we know that its acceleration is 9.8 meters per second squared in the downward direction. And because I'm telling you that the ball was dropped, we know that v1 equals 0. Okay? Notice how the spacing between the lines gets greater and greater as time goes by. In the beginning, the lines are really closely spaced, the vertical spacing of these lines. But as you get further down, they get much further apart. That is, of course, indicative of this, the acceleration. Okay? Now let's take a look at the lighter colored ball. Maybe I'll highlight this in blue just to help you keep track. what do you notice about this ball's progress in the vertical direction? Notice how it exactly parallels the dropped ball. So for example, at any given moment, the vertical progress of the colored ball is the same as the vertical progress of the white ball, which is telling you that in the y direction, for this ball here, the acceleration is also 9.8 meters per second squared down. And now this is a very important observation, because what this is telling you is that it doesn't matter whether you project something horizontally or whether you just drop it. It will progress vertically at the same rate, namely the rate of acceleration due to gravity. Now, to help you really understand this point, I want you to do a little thought experiment in your mind. I want you to picture yourself out on the soccer field at the school. So there's a lot of space to move around, and we know that the ground is very level. Okay? Now imagine that you and your lab partner are standing beside one another, and imagine that you guys are the same height. Okay? Now, your lab partner has a gun, let's say. Now don't worry, he's not going to do anything bad with it. We're going to do a little bit of physics here. He takes the gun and he holds it straight out in his arms and points it straight across the field. That way, we know that when he pulls the trigger, the bullet will exit the gun traveling horizontally, just like along this path over here, circled blue. Now what your job is to take an identical bullet to the one that's in the gun and hold it at the same level as the gun, and the instant you hear the gun go off, and therefore you know the bullet has been fired horizontally, you're going to take your bullet and just drop it. So you're going to be simulating the red highlighted area here. And my question to you is this: which bullet hits the ground first? Is it the bullet fired out of the gun? That would be analogous to this. Or is it the bullet that was dropped from your hand? That would be analogous to this. So which one hits the ground first? Now, I sometimes ask students this in class before I show them this picture, and quite often people think that the bullet fired out of the gun stays in the air longer. They feel that because it's moving horizontally, it somehow resists falling more effectively than any dropped object. And, well, it's fancy thinking, but this picture tells you that it's wrong. This picture tells you that both bullets fall at the same rate, especially if we neglect air resistance. Now, in fairness, when there is air resistance, which there certainly would be if you had a bullet going so fast through the air, there might be other effects, such as lift acting on the bullet. We're not going to talk about that because we're talking about no air resistance, okay? But it is interesting to note that, you know, think to yourself, what would you have answered if I asked you this gun question before you saw this picture? How many of you would have thought, you know what, I think I might have answered that the fired bullet lands after the dropped bullet? Well, this tells us something else. There's one more thing to note from this picture, which is that if you look at the horizontally launched ball, it's making its progress horizontally, as noted by these lines, at a very, very steady pace. Each of these neighboring lines they're equally spaced, aren't they? What's that telling you? It's telling you that in the x direction, the velocity is constant. And actually, we're going to call that Vx. All right? So notice, the velocity is constant in the x direction, but it's accelerated in the y direction. This means that projectile motion is a little tricky. It's got two kinds of motion. It's got the accelerated y motion and the constant velocity x motion. Your job is to combine these two motions using kinematics in order to figure out an answer to the question of what is the projectile doing? How do we make calculations for projectiles? Have to apologize for the announcement. I am recording this at school, and there's a lot of announcements these days for timetable changes, so I'm just going to keep talking over that announcement. Good, it's over. Let's take a look at a question from the textbook now. This question is number 4. It is, I believe, on page 46 in your textbook. Just going to check that. Yes, it is. So this is 4 on page 46 of the Nelson Physics 12 book. It says a stone is thrown horizontally with an initial speed of 8 meters per second from a cliff. So first off, I'm going to draw this. As you know from being in my class, you never do a question without a diagram. It's really a bad idea to not do a diagram. You're really making it hard to solve things. Try to get those lines as straight as I can. Okay, so here goes. I'm going to try to draw a stone. Okay, here's my stone. See, you don't have to be a good artist. That's the best I can do. It's fired initially at 8 meters per second from a cliff horizontally. So maybe what I'll do is just indicate this with a line going as straight across as I can. There we go. Okay, great. And this is going to be what we call V1, or V initial, 8 meters per second to the right. Now I know that this stone is obviously going to move to the right and it's going to move downward. So I should start thinking about designating a positive and a negative direction for both x and y. And the way I'm going to do that is by writing this. Positive to the right and positive down. This will be positive x, this will be positive y. I'm going to make y positive in the downward direction because nothing's going up in this question, so let's try to avoid negative numbers by doing that. Okay? Now what happens to the stone as it goes? It follows a curved path, as you saw in the picture over here, right? This is some sort of curve, as I'm sure you can imagine, or if you prefer, you could look at this, where the guy is going on some sort of curve. We'll find out later what actual curve it is. Is it a circular path or some other path? We'll find out. But this is kind of what you're expecting. And so to just get started like this is not a bad thing. We can also write in some of the things we know. Acceleration in the y direction is positive for downwards, so positive 9.8 meters per second squared. Okay? And what else can we write? Well, we know that if the stone was thrown horizontally, which is what they say, then it was given no initial vertical component to its velocity. So we actually do know that v1 in the y direction is 0. Again, it's a horizontal launch. Initially, there's no y velocity. And for that matter, since all of the initial velocity was in the x direction, that means that v1 is actually our vx, which, if you recall, is constant. So for the entire problem, Vx will be constant at 8 meters per second. Vy will start at 0, but thinking back to this picture, the y velocity will begin to increase as we accelerate according to 9.8. So now getting back here, is there anything else we know? Well, they ask you to determine the horizontal and vertical components of displacement and instantaneous velocity at times of 0, 1, 2, and 3, and so on seconds. So how are we going to go about doing this? Well, what I'm going to do is create a little table here, and I probably should have done this beforehand. However, I'm going to do it now. Whoops, I want to get that in a little bit easier to see. So I'm going to do that in black there. Here's a data table that I'm going to try to produce for you. All right. First off, we're going to start with the time. So we'll make a little column here and make a little row there. Okay, so first off, we're going to have the time value in seconds. And we're going to start off with 0. And then what we're going to do is write down what is the x component of velocity measured in meters per second. And I'll draw a little line here. At time 0, the initial x velocity, well, we talked about how it's actually constant, so we can write in 8. And therefore, after an entire 0 seconds, so in other words, before you've even gone anywhere, what is your delta dx measured in meters? Well, no time, you haven't gone anywhere. And now we're going to start talking about the y values. So what is the initial y velocity in meters per second? And let's close that off like this. Well, like we said in the beginning, for a horizontal launch, there is no y velocity, no y component. So we have that. And finally, what is the delta dy measured in meters? Well, again, you haven't gone anywhere, so 0. Wasn't that easy? That's about as easy as it gets, unfortunately. There's not much doing at time 0. Where things get interesting is at time 1 second. What has happened after 1 second? Well, let's look at what we know about projectiles. The x velocity remains the same. It is constant. Now, if you move at 8 meters per second, constant for 1 second, how far will you go? That's distance equals speed times time. That's a formula for constant speed. So we just do 8 times 1, and we get 8 meters is as far as you've gone. How about in the y direction? After 1 second, what has happened? Well, here's where you got to think back to this picture here. In the y direction, you accelerate at 9.8. And therefore, what formula can you use for acceleration and velocity? Well, actually, we know this. v2 equals v1 plus a delta t, but in the y direction. So put a little subscript y down there. And what are you going to get? V final in the y direction will be v initial, which was 0, plus the 9.8 acceleration, positive, because we said positive was down. 1 second has gone by. You're moving at 9.8 meters per second in the y direction after that 1 second. And how far have you gone? Well, a formula for displacement when there's acceleration, delta dy equals v1y delta t plus a half ay. Oops, that doesn't look like a y. Ay delta t squared. Once again, initial y velocity 0, add in a half of a delta t squared, and if you run that through your calculator, you get a 4.9, as in 4.9 meters. So we have answered at least the first part of the question, determine the horizontal and vertical displacements and velocities at 0 and 1 second. Now, what do these look like? Let's go back to this diagram here and try to draw those in. At the 1 second mark, I have to somehow show on my diagram, and I should try to show this as carefully as possible, that I have done the following. I have physically moved 8 meters to the right in the x direction, but I've physically moved down only 4.9 meters in the y direction. So I should probably draw maybe right there, and perhaps what I can do maybe in, let's see what color I can use here, maybe, actually let's use magenta or something. I haven't used that in a while. How can I show you here that I've moved across, oops, I've moved across a delta dx of 8 meters, and I've moved down a delta dy of only 4.9 meters. So that's what these numbers correspond to. And you can see my diagram looks, it's not to scale, but it's certainly realistic in that the 8 meter line is longer than the 4.9. These are the displacements so far. Okay? Now let's take a look at the velocities that we have. We have two components. One is the x component, still 8 meters per second. Now I drew that in red previously, and things are going to start to get a little crowded here, so here's what I'm going to do. I'm going to erase this. What did that say? That said v1y is 0, and it was written in red. So I'm going to go back and put that in there. v1y equals 0. Okay, so I've just moved that over. What I want to show you now are the velocity vectors, where you can see that we're still moving horizontally about 8 meters per second, so these two vector lines are about the same. However, my y velocity has increased from 0 all the way to 9.8, down. And therefore, I've got a downward velocity here looking something like that, a little bit longer than the 8 meter per second velocity vector that is over there. Now remember, these guys meet at a right angle, and if you add your Vx and your Vy, you will get what's called your V instantaneous. So let's just go down there. This is what we call V instantaneous at t equals 1 second. It's got a direction, some angle below the horizontal, and it's got a magnitude, and you guys know how to solve for that. For the magnitude, we use Pythagorean theorem. It's going to be the square root of 8 squared plus 9.8 squared. And what does that come to? I should have my calculator with me, and of course I don't have it with me. Well, I'm going to leave it to you guys to do this while I race with you. I've left my calculator at the other end of the room, so I'm going to try this on my smartphone, which is not the best way to do it, but hey, what can you do? What do I get here? If I do 8 and I square it, and I add to that 9.8 and I square it, I get 160, and then I'm going to raise that to the exponent a half. Okay, I get a number of 12.65 meters per second. And I also need a direction. And how am I going to get direction? I'm going to do tan theta equals opposite over adjacent. That's 9.8 over 8. And what's that going to give me as theta? Once again, on my calculator here, I'm going to need the tan inverse. So that'll be second function tan, open some brackets, and I need 9.8 divided by 8. Close that bracket, see what I get. And my calculator's given me a hassle here. I've never used the scientific function on my smartphone calculator, so bear with me, folks. Let's see, 9.8. You guys are probably ahead of this by now. So I got 1.225, and I need the second. I need the tan inverse. There we go. I got 50.8 degrees, or 50.77 to 2 decimal places. Okay? So what's that telling you? That's telling you that your instantaneous velocity is 12.65 meters per second. And we could say something like right 50.77 degrees down. Now, of course, you should be careful about your sig figs here. I'm kind of being sloppy with sig figs because I just want you to focus on the new physics here of projectile motion calculations. But that's basically it. You've seen now how at 2 different times we can take into account the changing or constant velocities and the always changing displacements, how we can combine them to see where the object is, and how we can combine the velocities to see how fast it's going. Now, a couple of other things that the question asks you to do. They ask you to keep on going for a time of 2 seconds and 3 seconds. So what I'd like you to do on your own now is continue this chart with times of 2 and 3 in another row. Your Vx's will stay constant, but your delta Dx's will be going up by 8 meters every second. Your Vy's are increasing by 9.8 meters per second each second, so this number should grow. And your delta Dy's are increasing every second by quite a bit, by a half of a delta t squared, so make sure you calculate those. And what I'd like you to do is redraw this diagram bigger and add, sort of label in everything that you see. They ask you to do it with a scale diagram. I'll make you a deal. If you agree to draw diagrams, then you don't have to use a scale diagram. That would take you a while, but you definitely need a diagram. We've answered part C, draw the instantaneous velocity vector. We didn't do it at each point in the diagram. We did it at the 1 second mark, but I'm going to leave it to you to do it at the 2 and the 3 second mark. And finally, here's a little bit of a challenge before you leave. What is the average acceleration between 1 and 2 seconds, between 2 and 3 seconds? Well, here's a little hint for that. When you're finding the average acceleration, you need to remember the formula. AAV equals V2 minus V1 over delta t. So let's say you're calculating this from t equals 2 seconds to 3 seconds. That was one of their questions. So here's what I'd like you to do. At t equals 2 seconds, I want you to write down what is the velocity x comma y. And at 3 seconds, what is the velocity x comma y. Since this is the earlier time, we'll call this the initial velocity. Since this is the later time, we'll call it the final velocity. where are you going to get these x and y components from? Well, if you did your chart correctly, they should already be done for you because, sorry, there's the bell, it's the end of the period. I'm going to have to sign off in a minute. But if you did this chart correctly, here are your x components of velocity. They stay the same. So right away, we just put in 8 there. That was easy. What are your y components? We'll go back here and look at the y components. At 1 second, it was 9.8. What's it going to be at 2? What's it going to be at 3? That's your job to figure out. I'm leaving that to you as an exercise. And so once you have all of these written in, do what the formula tells you to do. It tells you to take V2 and subtract V1 and see what you get. What are you going to get as your final x and y components? Figure out their magnitude of this vector and figure out the direction, and then answer the question, determine the average acceleration. I think you will maybe be surprised, but at the same time not be surprised when you think about it, what this answer comes to. All right, folks, that's it for the intro to projectile motion for horizontal launches. The only question we didn't answer is what is the shape of the path that this projectile takes. So what is the path's shape? We're also going to answer this in class, although I'd like you to think about it and pause the video. I guess I'll give it to you now so that I'll let you off the hook. But pause the video and think about it. What is the shape? Okay, pause now. Come back when you're ready. Okay, and so here's the thought. You know that the shape was kind of curved. We don't know if it's circular or not. I'll give you a hint. The horizontal motion was at a steady rate. The vertical motion kept getting longer and longer, and the equation for this had 1/2 a delta t squared in it, if you think back to our chart. And the formula here just had speed times time, right? So this one is increasing linearly. This is increasing quadratically. Do you know what the shape is now? If you guessed parabola, you're right. This is basically a math equation of y equals, well, a negative x squared sort of deal. So welcome to projectile motion. We've learned that the parabola is the shape of the trajectory or the path. We've also learned how to do all of our calculations on these 2 pages here, how to use components, and we've also learned some important insights about projectile motion. All right, so stay tuned for the last video or the second video, part 2, where we'll deal with non-horizontal launches. Thanks for watching.